how hard it is to stop an object from spinning or rotating. Now, the formula for angular momentum. Here's my big formula. L equals I omega. Now, we have seen something very close to this with torque equals I alpha, right? So you got to think there's got to be some relationship between torque and angular momentum through inertia, right? Yeah. And we'll look at that in a minute. So what are the units? Guys, the units for inertia is kilogram meters squared, isn't it? So inertia's got units of kilogram meters squared. Omega is meters per what? I'm sorry, hang on. Radians per second, yeah, excuse me. Here it is. Is it kilogram meters squared or kilograms meters? Inertia. MR squared. So it's meter squared. Kilogram meter squared. Do you see I figured out what the units were? What's the formula we said, the basic formula for inertia? MR squared, right? Mass is kilograms, R is meters, right? So it's kilogram meter squared. And omega is radians per second. Okay? So our units here are going to be kilogram meters squared per second. And that is for L. So these are my units for L. Now, angular impulse. Do you remember what we said impulse was for linear motion? What is it? By definition, what is it? All right, for a very small period of time, yes, it's a force that acts over, it's change in what? That's what I wanted. It is change in linear momentum, isn't it? I for impulse was equal to change in linear momentum. Angular momentum is then change in what? Angular momentum, yeah. So angular impulse is the change in angular momentum. J is equal to delta L. Okay? Now, it is also equal to this. Torque times time. Do you know why it's equal to torque? Can we have a change in rotation without a torque acting on something? I want you to think about that. If we want the thing to quit spinning or to change the rate at which it spins, don't we need to apply a radial force to it somehow to either slow it down or speed it up? That would be a torque. How long we apply it tells us how rapidly or slowly it slows down, right? That's our impulse factor. Time is always part of impulse. So now we've got this way to relate linear or a rotational momentum, angular momentum with angular impulse and torque. All right, so let's look at what we know here. And then we'll talk about actually feeling some of this angular momentum. Angular momentum is a cross product. Remember how we used the right-hand rule for a couple of things? This is also a right-hand rule. If we apply the angular momentum, if it's rotating this way, guess what's happening? The torque is being applied this way, isn't it? The thing is rotating in the XY. Guess which way the angular momentum is going? In the direction of your thumb. So if the object is rotating counterclockwise, the angular momentum is positive and up. If the object is rotating clockwise, the angular momentum is down and negative. But you can kind of feel that when you, and we're just going to go ahead and do this so you guys can kind of tell. If you take this guy and you start really spinning it, and you start to move it up or down, it's hard to move it up or down. And if I take and just hold it like this, you can actually see that it's going to do what we call process. But it's, what you're seeing is that angular momentum coming out this way, and as I'm holding it on the end here, because it's wobbling a little bit, that's what's causing it to process. It's causing that vector right here to move in its own shape. It's kind of fun. As it wiggles, it does that. But you can actually feel how hard it is to move it when you touch it. It's very strange. And if we pull down, matter of fact, I'm going to combine the two things we did yesterday. Y'all, take a second, grab one of these, grab it by the handle, actually spin it, and take a minute to actually feel how hard it is to move it. I want everybody to try this. So just pass around, two of them, pass around and see how hard it is. And then I'll show you why we know the angular momentum is this way. Okay? That it's an actual physical quantity that you can't tell, but you'll be able to in just a second. I should have just left my rotating. Here it is. Back on the rotating platform, and I'm gonna prove to you that it actually is going the direction you think it's going, or unless somebody else wants to rotate today.
Get on there, Dylan. Get on there.
I can't.
Yes, you can.
All right, so here, hold on. Just stand on it. It'll be all right. Hold this, and I'm gonna spin this. Now, move it. Move that. Now. Notice as he's moving, don't move the rest of you, just move this sideways. Move it this way. You feel like you're fixing to rotate, because you are. Now as he moves it, all right, step down before you kill yourself. All right, so as we stand up here, first time I've done this without with my knee. I got this. As you stand on this to rotate it, if I want to move that way, all I have to do is change the direction of the wheel. Now look what's happening as I change the direction of the wheel. Now I'm moving it this way. What direction am I going to end up? Look at that. Now look what's happening. I'm not doing anything except very strange, but do you see how it's pushing me? It's pushing me, isn't it? And now it's pushing me the other way. Very strange. I'm changing the momentum. Now, why is it facing up, moving me this way? The angular momentum is not what's moving me. What's moving me is the torquing force that's causing the wheel to rotate, isn't it? So as I move it up, now all of a sudden my torque is pushing this way, isn't it? And if I move it down, oh, look at that! Now it's pushing me the other direction, isn't it?
Physics is mind-blowing.
It is.
It's really mind-blowing.
That's why I think it's so much fun, is it is mind-blowing, but it's true. So you've got this torquing force, but we're changing the momentum very quickly. That impulse is changing, and it's causing me to rotate. It's very strange, isn't it? Anybody else want to try it? It is cool. That one's even heavier, so that one will actually move you even more and faster if you get on the platform.
I'm gonna try that.
Now move it up and down. Look at that. Now he's moving. Isn't it cool? So we're creating a change. We're creating an angular impulse. And then the torque that's causing the angular momentum is pushing him, just like it's acting on the wheel. Okay? Kind of cool. Physics in action. Things you don't believe unless you actually see it. Get off your phones. Shouldn't be on your phones anyway. And the harder you spin it, the harder it is to make it move directions, isn't it? Really spin it hard and try to, like Manny's doing, spin it really, really hard and then try to change directions. That's a good spin. Now you're really going around. And now you're changing the direction of the torque, and so now it's moving you the other way. Yeah. It's kind of cool. It's so gentle. You're going around so gently, it doesn't make you dizzy or anything. Huh? It depends on if they're both going the same direction or not. If you got one going one way and one going the other way, what's going to happen? They should.
Yeah, I'm going to spin. Which way is it going? This way? No, this one's going this way, and this one the other way. Or do you want them both?
Miss Duffy, have you got a road?
Yeah.
That's
Yep. Now you're really going.
Put them in different directions.
And look,
Oh, wow.
now he came to a stop.
Well, this one's a little bit.
It is. So he's still moving just a little bit, but now he's really moving. Careful with the rope. You get it tangled up and then you'll come off that thing. All right. So let's move on. You've all got to experience some. Did everybody get a chance to feel the angular momentum and look and feel the torque acting and that angular impulse as you try to move that wheel? The thing you're feeling when you're holding it and it's spinning like this and you go to move it up and down, if the faster it's spinning, the harder it is to move, isn't it? Yeah, it means that it's a stronger impulse that's happening when you do actually get it to move. That actual moving it this way is a change in angular momentum, isn't it? Because we're changing the angle. So that's what's causing that impulse to happen. All right, so let's look at, you having fun there? You can just stand on it and spin all day. I mean, it's actually kind of somewhat soothing. No, you can't. You got to take notes. I hope this helps you understand a little bit better kind of what we're talking about. Actually seeing it in motion, the body moving, it's kind of cool. So, all right. So, a uniform 3-kilogram rod is 2 meters long, rotates about its center. So, here's my center pivot point. By the hammer of Thor, the rod is struck by a 1,500 Newton force for 0.8 seconds, directed perpendicular to the rod. It's important that it's directed perpendicular. Why?
So that the full force actually goes on.
So it's a full force for the torque, right? Okay. What's the angular velocity? So we are looking for omega of the rod after impact. And I for the rod pivot center is this. So see what I mean about they'll usually give you I if you need it? All right, so we're going to set this up. We know about impulse, right? How do we know we actually had an impulse? We've got a force that's being struck what? A very short period of time, right? Okay. So what we know is this. We've got an angular impulse. We know that's change in angular momentum. Okay. This is equal to torque times time. You know why I know I needed torque and time? That force, right? And it gave me a time. And I know impulse. Anytime I think impulse, I have to think, okay, what short time? That's equal to angular momentum, change in angular momentum. Well, change in angular momentum is going to be L final minus L initial, isn't it? Well, guys, that is, what's the formula for L? I what? I omega. It is I omega. So this is I omega final minus I omega initial, isn't it? Now, how do I know the I is still the same? for both of those? Did the object shape change? Did its pivot change where its pivot was change? So it's just I, isn't it? So we could pull the I out if we wanted to, but it doesn't matter because what do we know? What do we know about omega initial? It's 0, isn't it? So that part goes away. What do we know about torque? How do we define torque? Force times the radius, and then times time. So that's going to be FRT equals I omega final. And that's what we're looking for, isn't it? Aren't we actually looking for omega final? So now all we have to do is plug some stuff in, don't we? So what is my force? You better be careful. 1,500 newtons, you are correct. The force is 1,500 newtons, but it's going this way, isn't it? Which means this thing is what? Rotating clockwise, correct? So this is negative 1,500. How far away is it from the center? It is a 2 meter long rod, so it is from here to here, it is 1 meter. And what's the time? And now we need to plug in I. I is this guy right here, isn't it? So we're going to come down and plug that in for I. 1 over 12. The mass was 3. And what's the length of the rod? This is the full length this time, isn't it? So this will be 2 squared. And then we do omega final. So if you know the formulas, you'll be okay on this. So let's start doing some calculations. So I got negative 120 on this side. And I got 4 times 3 is 12, divided by 12. Ooh, that goes away. Look at that. Boom. And what are the units going to be for this? Radians per second.
Wouldn't that be 2 revolutions? No, 15.
No, it's 2 pi, not 2. So if you got 120 radians per second, you could change radians into revolutions. 1 revolution is 2 pi. So it's more like 6. So 125 is about 20 revolutions per second.
It's really high.
Still pretty high, isn't it? 20 goes around 20 times every second. That's really, well, I mean, Thor's hammer. I mean, come on. If we're in the Marvel universe, we might as well be hitting it with Thor's hammer and hitting it hard. Thor hits the end of it, it might go 20 revolutions in a second. Would you want to try to catch it and stop it? No. It's a pretty high impulse, isn't it? Yes. All right, so let's talk about conservation of angular momentum. Just like we had conservation of linear momentum, we've got conservation of angular momentum. Angular momentum is always conserved unless what? In other words, as long as we don't disturb the rotation by poking it, trying to get it to stop, slow down, or speed up, right? As long as the wheel is just spinning. External torque. This is an external torque being applied. So now there's no external torque being applied, is there? If I want to apply an external torque, I have to, stop it, don't I? Now, is angular momentum being conserved? Clearly not. It slowed down, didn't it? So as long as we're not, and I just applied another external torque. As long as I'm not doing anything but letting it sit here and it's frictionless at the wheel, at the axle, it should just keep turning and turning and turning and turning forever. Should it? Conservation of angular momentum. Now it's not going to because this is not perfect. It will go for quite a while. But there's always going to be a little friction, isn't there? Yeah. All right.
So where would it come
the bearings rubbing against the axle. That's why we have to grease the bearings in an axle that are connected to an axle. You know, if you've ever put anything together, like your tire rotates, etc., if your bearings don't stay greased, your axle's going to heat up and lock up, and it's going to be ugly. You have to keep it lubricated. Otherwise, and the better the lubrication is, that's why we spend so much time and energy and money. That's why places like 3M make tons and tons of money for making things like that make things spin more frictionless. Because the less friction there is, the less energy you're using. So all the rotational energy that goes in, you come back out again. All right? That's why substances like silicone and white grease, like we use in cars, can be kind of expensive and are very lucrative because they are really good at reducing friction between two surfaces. All right, so L is always conserved in an isolated system. I want you to think about what that means. Isolated system means there's no external torques acting, isn't there? No net external torques. Net equals 0 here, right? Okay, so what that means is that whatever goes in is what comes out. Now, why do we say net external torques? Internal torques don't change the momentum. Think about why that would be. Internal torques are going to be technically what we defined as 0 away from the axis of rotation, wouldn't they? They're not going to create any real torque influence on what's happening with the rotation. Okay? All right. So let's cruise on and actually do a little bit of problem solving here. Here we go. We haven't learned anything ground shaking except we've learned a couple new formulas, right? L final equals L initial and L equals I omega. That one's a big one. Check your formula sheet. Is L equals I omega on your formula sheet? If it is, that means it must be a very important formula in physics. Yep. It's there. Is J in there? Change in impulse? You sure? Impulse equals, let me look.
I don't think we have a J coefficient at all.
No, but change in angular momentum is T delta T, was torque times delta T. And do I have any impulse formulas on here at all? That's making me crazy. Okay, then I guess you have to know that one. Just like you had to know change in big I impulse, linear impulse is delta P, right? So angular impulse is delta L. All right. Baggage carousel has a mass of 500 kilograms and is in the shape of a disc with a radius of 2 meters. So we've got a disc rotating about a center. And it's going to rotate at 1 radian per second. Okay? Then it says 10 pieces of luggage with a mass of 20 kilograms, average mass of 20 kilograms are dropped onto the carousel. So if you have 10 pieces of luggage, average of 20 each, that's 200 kilograms, isn't it, of mass? So we're going to chunk 200 milligrams down here, or kilograms, excuse me, down there on the carousel. And then it says, find the speed of the carousel after the luggage is added if no external torques act on the carousel. This fact that they say no external torques act tells us that what? L initial equals L final. That's what that statement tells you right there. It means you can use conservation of angular momentum. What that means is the following, guys. This is I omega, isn't it? So this is I initial, omega initial equals I final, omega final. Now I can't just say I and I this time. Can anybody tell me why I can't just mark I out?
Because the inertia changed since you have more mass on the outside.
Yeah, it's changing because we're dropping mass on it, aren't we? So the luggage is going to also have some inertia because it's not being dropped on the rotational axis. It's being dropped out somewhere along the edge, isn't it? Okay, so here we go. Let's find this. So what is the initial... What's the formula for the inertia of a disk? I gave you all those inertia formulas, right? 1/2. It's 1/2 mr squared, isn't it? A solid disk?
1/2 mr squared.
Okay, so this is going to be 1/2 mr squared here times omega initial. Now, let's talk about I final. I final is going to be the combination of the 1/2 mr squared plus what? So this is the actual cart, right? Or carousel. 10 times mr squared, right? Wouldn't each piece of luggage be a point mass? Point mass is mr squared. And this is for the luggage. Times omega final. So let's start plugging in. See what we get. 1/2. Mass of the carousel is going to be what, 500? Okay. What is the radius of the carousel? 2 meters. And what is the initial rotational rate? 1 radian per second. Now we got to finish this up. So let's do this side. Let's go ahead and do some calculations as we go. So we have 500 times 4 divided by 2. It's 1,000, right? We've got 1,000 on this side. All right, so now we got to do this carousel. So we know this is 1,000 because we just found that, plus 10 times 1 bag. So how big is 1 bag? 20, and it's sitting out along the edge, isn't it? So that is 2 squared. And this is times what? Omega final, which is what we're looking for, isn't it? Let me separate that so you can tell they're not together. So 10 times 20 times 4 plus that 1,000, 1,800 omega final. So omega final is what? 0.56 radians per second. It's not the neatest thing in the world, but it's not terribly hard. What was the hardest part about this entire problem?
Finding the inertia for the...
Yeah. And if this had been an AP question, they would have given you the inertia for the carousel. What they wouldn't have given you is the inertia formula for the baggage, because you need to know a point mass, huh?
It'd probably be knowing that it was a point mass. Because I probably just overlooked that and be like, add the weight together.
Yeah. Knowing that it's a point mass would have to be something you would need to know. So let's make a note of that. If you've got 10 pieces of luggage like this that are being dropped, this is a point mass, right? So the inertia is mr squared. So we can make notes in our types of problems that we do. That helps us. Guys, do you realize that if something is moving, if you've got a point right here, and you've got an object right here that's a mass, and it is moving with some velocity past something, that it creates an angular momentum? Did you realize that? So if I stand here, and Jalen runs by me in the room over there, believe it or not, he's created angular momentum between the two of us. I have acted angular momentum because he's moving. He has created angular momentum on me. Yeah, as he goes by me. Even, they don't necessarily feel it, but because it's so small, isn't it? Comparatively speaking. But every planet that moves by, or every asteroid that goes by, anything that's moving in space that moves by something else that's in space creates angular momentum. It may just be so small we don't really feel it. But if you get enough velocity and you get enough movement past you, you do feel it. It's very strange, but that's the way things work. So what we have to know is where the point is. So this is my point mass. Hang on. Why am I not? Really? Why is this dying? All right. Give me a sec, guys. You ever had one of those days? I came in here first block and tried to get it to broadcast up there, and it was just a blank screen. Spent the first 10 minutes of class trying to figure out why it wouldn't project anymore. We finally got that fixed. Don't know why it did it in the first place. I had to turn my iPad off, turn it back on, turn the projector off, turn it back on. It all takes time. And now, the pencil. Pain in the butt. All right, this is the radius. This is the R we're talking about here. Okay, that's the distance. Think about why that is. What we're getting is we get some sort of torque being applied, don't we? As it's moving. So this gives us angular momentum. How do we split between angular momentum and linear momentum? Because this guy, if it's going MV, this is linear momentum, isn't it? Would you agree? Maybe we should call this an O for origin. That linear momentum of an object going by at a velocity, a mass moving at a velocity, causes an angular momentum. Do you remember how we switched between all the other types of linear versus angular? Do you remember? We multiplied by what? To get the angular, we multiplied the linear by R, didn't we? Think about it. Didn't we know?
Excuse me, Miss Dusty?
Yeah?
May I see Sam Crawford when it's good for you with his Chromebook, please?
Sure.
Thanks.
Didn't we find that? Didn't we find this? Yes? Yeah, we did, didn't we? Didn't we find this? Yeah, we did, didn't we? All of those things we found. All right. So, guess what angular momentum can be defined as? Linear momentum times R. And linear momentum is mv, isn't it? So here's another version of the formula, mvr, to change between linear momentum and angular momentum. To get angular momentum, if we have linear momentum, we simply have to multiply by the distance the object that has got that linear momentum is away from the object that it's influencing. Okay? This is that r right here. This r right here is this distance away right there. That's perpendicular. It's the perpendicular distance away. All right? So now, what if you have a collision that's got rotation in it? Then you will have you have conservation of both what? Linear momentum and angular momentum. Think about it. If you can change linear momentum to angular momentum by just including r, if a linear momentum is conserved, doesn't it automatically mean angular momentum would be conserved? Yeah, we're just changing, we're literally just multiplying everything through by r, and we're getting our angular momentum conservation law out of it. Get what I'm saying? Yeah. All right, so let's work some more examples, and let's see what we got here. We got example C. We have a bullet of mass 20.2 kilograms. Shot at a 40 kilogram door at its unhinged end. Speed of the bullet is initially 200 meters per second. So we've got an initial, we've got mass, we've got 40 kilogram door. We know it's hinged. Travels perpendicular to the plane of the door. Why is that important? Full force, yep. Bullet becomes embedded in the door, and then it gives us the area of the door, doesn't it? It says, what's the angular velocity of the door after the door after the bullet strikes? There's extra words in there. It happened twice. After the bullet strikes. The door is a rod hinged at one end, so they've given us the inertia formula, haven't they? Guys, if they give us an inertia formula, don't you think that means we ought to what? Yeah, use it at some point. So if you work through the entire problem and you never use that inertia formula, guess what? You probably did something wrong. That's a big old hint right there. So before the collision, what do we know? If we're looking at this from the top, we have a door, we have a hinge, don't we? This is before a collision. And we have some bullet going this way, towards the edge of the door. After the collision, what's happening with the door? Yeah, it is swinging this way, isn't it? With some sort of angular velocity. All right. We know they have told us collision. How have they told us collision? Yeah, becomes embedded in the door. This tells me collision. We know something is swinging, don't we? Therefore, we have a collision and we have rotation, which means what is conserved? Angular momentum. Why are we using angular this time and not linear? Because the door is swinging around in an arc, isn't it? So can you tell now how you tell the difference between the two? Yeah? Okay. So now what's the formula? Initial angular momentum, what do we know? We know the mass of the door, don't we? Initially the mass of the door is that. Do we know the velocity of the door? We don't know anything yet. Yes, of the door. But we also need to know what? What's the only thing? Remember, we've got two things moving here. We got the door and the bullet. Which one of these things is the only thing that's moving? The bullet. So all the initial angular velocity is in the bullet. So this is going to be the mass of the bullet times the initial velocity of the bullet times how far away from the hinge it is, right? Isn't that what R is? Now afterwards, what's moving? The door and the bullet, right? How did I know to use that formula on one side and the other formula on the other? Yeah. It went from linear momentum to angular momentum, didn't it? But this formula right here, here's my linear part. Tacking the r on the end changed it from linear to angular so we could have them the same on both sides. Does that make sense to everybody? So now we can start plugging in. All right, so let's do this. Mass of the bullet is what? What was the initial velocity of the bullet? And how far away from the door was it? There's a question. Look right down here.
1.5 meters away.
Yes, it would be this. Unhinged end. If the door is so many tall, this would be how long it is, wouldn't it? This is 1.5 meters. That's the only part we need. Now, how do we find the inertia of the door and the inertia of the bullet? Those are two separate pieces, aren't they? Didn't it give us the formula for the door? Look. So this is going to be 1/3, and the bullet is what? A point mass. The bullet is small enough, it's a point mass. So you can see how this is going to work. So 1/3 the mass of the door, which was 40 kilograms, right? Times width of the door, 1.5 squared, plus, let me get to where I can actually write this out, mr squared, right? That mr squared, though, is going to be the bullet, isn't it? So, mass of the bullet, 0.2, r squared is 1.5 squared, and then that's omega. So it's just a bunch of numbers we need to multiply, isn't it? Did I lose anybody down here in the weeds? This is the door. This is the bullet. So let's see if we can figure out what this is. 0.2 times 200 times 1.5. Want to wait? $40 times 1.5 squared divided by 3 gives me 30 plus 0.45, and that's times omega. You got what?
60.
Where, instead of 108?
Over 0.2 times 200 times 1.5.
0.2 times 200 times 1.5 is 60. I don't know where 108 came from. Calculator user error, huh? 60. Come on.
I got 6.
All right. Did my other calculations work? Did you get 1.97? And that would be radians per second? Should be. All right, so now here's the hard part of the question. How would the answer change if the bullet hit closer to the door and not at the edge? What would happen?
Less torque.
R for the bullet would do what?
Go down.
Go down, which means that the inertia for the bullet and L initial would both what? They would both go down. So if L initial goes down, then L final, which is equal, also does what?
Oh, mine goes down.
Goes down, doesn't it? So L final also goes down. So what does that do to the rate at which the velocity at which it swings around? It's less, isn't it? So if L final goes down, now the rotational velocity also goes down. In other words, what does that mean? It swings what?
Slow. Less speed.
Yeah, rotational velocity goes down. If L initial goes down, L final does go down, right? Less moment of inertia after the collision. We got that right. So yeah, it's going to rotate what? Slower. It's going to rotate slower, isn't it? Okay. So what have we learned today? What are our big moments today? Let's recap.
Linear momentum, or not angular momentum.
L initial equals L final, right? What are the formulas for L? L is what?
Torque times time.
Torque times the change in time. Good. What else is L?
Linear momentum times radius and VR.
MVR. Okay, what else is L?
Inertia times angular velocity.
So there's lots of different ways we can find L. What's the other big concept we talked about today? Angular what?
Angular impulse.
Angular impulse. And what is angular impulse?
It's linear impulse.
Change in angular momentum, isn't it? Guys, this is not, hang on. Is that right? I don't think so. No, I wrote it down when thinking about it. This is not, L does not equal torque times time. J equals torque times time.
Oh, yeah.
This is equal to torque times time. That's why I looked at it and went, wait a minute, that's not right. Once we put impulse down, I was like, no, that's not right. All right. So what all do we know? What causes something to rotate? A torque. What keeps it rotating is inertia. Now, if something is rotating because it had a torque, what is it producing? Angular momentum. All right? So they all kind of go together, don't they? A torque causes the rotation, and the rotation produces an angular momentum. All right? When do we have conservation of angular momentum? No. It doesn't say no outside torque. It says no net outside torques. So if I have an outside torque going this way and an outside torque going this way, they're both going to what? Cancel out. So would we still have conservation of angular momentum? Yeah, we would. All right, so no net outside torques. All right, you've got 6-4 to do. There's not very many exercises in 6-4. I think there's 8 problems. 9 problems? Is that it? No, I don't even think there's that many. There's 6. 6 problems of homework. I mean, come on, guys. You can do 6 problems of homework, can't you? I know, it's fun, isn't it?